Okay guys, so last week we were talking about Newton's second law. Okay, Newton's second law says that if there is a net force present, an unbalanced force present, then a mass will experience an acceleration. Okay, and we can calculate that net force by multiplying the mass times the acceleration, or by finding the vector sum of all forces. Okay, and we did a couple like that on Friday. We did the one that we had to do, tail to head stuff, and we had one that was a little more straightforward, but pushing the car. Okay, so pretty straightforward stuff. Today we're going to start looking at more complex systems involving Newton's second law. We're just going to kind of continue to progress with that over the next couple of weeks here. Okay, so here's a good way to kind of get back into the groove of it. This is about the easiest Newton's second law problem you will ever get in my class. So write it down and see if you can solve it for me. Okay, remembering that F net equals mass times acceleration. You will need nothing more here. But you should probably draw a free body diagram as well. Okay, the box, the mass, the forces. Okay. Okay, let's quickly go over this one. So, a lacrosse player exerts an average net horizontal force of 3 newtons. What did they give me there? Net force. Okay, they outright said average net force. Okay, they said it was horizontal only to basically tell you, hey, there's nothing to worry about vertically speaking. Okay, because our tendency is to go, I got to analyze this. There must be a downward force because gravity is always present. Sure, gravity's present, but they told you the net force is horizontal. So that means there's no net force in which direction? Up or down. Okay, if they told you average net horizontal force, the object's only accelerating horizontally. And we're only talking about the time it's in the net of the lacrosse stick. Okay, or whatever they call it, racket, I don't know. It's a stick with a net on it. Okay, so while it's in there and he's exerting the force on it, right? That's the only part we're worried about. We're not worried about after it leaves. Yes, then gravity would be part of it. It'd be a projectile. We're only worried about during the passing attempt. Okay, so I don't need to draw these on there because they don't matter. The question outright told me F net equals 3 newtons, okay, horizontally. And they also tell me the mass. Okay, they tell me the mass of the lacrosse ball is 0.15 kilograms. Okay, so F net equals m times a. I'm trying to find a. So I'll divide both sides by mass. So that'll be 3.0 divided by 0.15. Okay, this is newtons. This is kilograms. Remember that a newton is a kilogram meter per second squared, so the kilograms are going to cancel. I'll be left with the units for acceleration, and it should be 20 meters per second squared forward on that one. Okay, everybody with me there? Okay. Any questions on that one? Again, that's as easy as they will ever get. Here's the net force, here's the mass, calculate the acceleration. The only way it could be easier is here's the mass, here's the acceleration, calculate the net force. Okay, they're never going to be that easy. It's just a good review from last week. All right, I want you guys to try these ones. They're all relatively easy. Okay, so you got 1 and 2 here. Okay, the answers are the numbers here in brackets. Okay, so you can check them as you go. They're very, very easy, like the one you just did. Okay, I want you to write this one down and try it. This one's more of a read it carefully, don't miss any details kind of question. Okay, so 2 athletes on a rowing team are training. Athlete A has a mass of 65 kilograms. Athlete B a mass of 70 kilograms. The canoe is a mass of 20. Okay, athlete A can exert a rowing force of 400 newtons forward and B a force of 420 newtons forward. In the water, there is a resisting force of 380 newtons. Okay, do I need to worry about gravity and normal force or buoyancy in this case and all of that? Last time I checked, canoes don't come out of the water when you row them. Okay? in this case, sure, gravity is there, but it's not important because the canoe is only moving horizontally, yeah, whatever direction is forward for it, okay? So you can consider that when you're drawing your free body diagram. It's great that you recognize gravity is there and that it's offset by normal force, but in a question like this where it's clearly horizontal, you don't necessarily need to identify or worry about them. So first thing we should do is draw our free body diagram, okay? What mass do I put inside the canoe? The total mass. Not just the canoe. That's the trick in this question. Remember, the two guys rowing it are also in there, and they have mass too. Okay, so it counts. So we got 85 and 70, 155. Is that right? Kilograms? Okay, so we got 155 kilograms worth of mass being pushed by two different forward forces. Okay, 400 newtons forward and 420 newtons forward, and resisted by 380 newtons. Okay, again, gravity and in this case buoyancy of the water are irrelevant because they cancel each other out. The boat is not floating off of the water. Okay, everyone all right with that? Okay, can I calculate the vector sum of all forces right now? Okay, absolutely I can. Okay, so we're looking at F net. Yes, it equals m times a, but I don't have enough information right now to calculate a. I need the net force first. Okay, so I'm going to go 400 plus 420, okay, plus 300 and plus negative 380. It's backwards. Okay, so I would treat it as a negative. Okay, so 820 minus 380 gives me 440 newtons. All right, so now I have the net force. Okay, I did the vector sum of all forces. Last week I told you in basically every Newton's second law question you do, you will do both a vector sum of all forces calculation and an F net equals m times a calculation. You might have to manipulate it like we do in this question for a, okay, but you're going to do one. So we'll have our 440 newtons divided by 155 kilograms worth of mass. Okay, so 440 divided by 155 gives us 2.84, no, sorry, we only have two significant digits, 2.8 meters per second squared, and I would say forward, because that's what we were given in the question. Okay, are little details important?
Yes.
Yeah, definitely. Okay, I mean, we're looking at this question, and the reason I put this one on there every single year is because it's a perfect example of, hey, did you think about the fact that there's two people in the canoe? Okay, it's like, that has nothing to do with your ability to do F net equals m times a. It has everything to do with, I can analyze a situation and see what all is involved. That's more important. I trust your ability to do these mathematical operations. That's no problem for you guys. It's interpreting and seeing what's involved in a question that's difficult. Okay? None of these are going to be terribly challenging mathematically. Okay? All right, try this one. There's a bunch of extraneous information in this question, but sometimes it's a little bit tricky to pick out what's important and what's not. Okay, so this is another one where we got to read it carefully because the first piece of information we get is useless. Okay, that's a regulation in the sport of bobsled. You cannot have a mass greater than 630 kilograms combined, sled and 4 people. In this question, are all 4 people in the sled? Nope. There's 2 people outside of the sled still pushing, right? In the 4-man or 4-woman bobsled, okay, what you usually see here for the athletes are people who were really good sprinters because they were really powerful, but they had no top speed, so they could never win in track and field. Okay, but they were super powerful, so they went into bobsled because it wasn't about your top speed; it was about how powerful you were. Okay, tons of failed sprinters become incredible bobsledders because they're very, very powerful. And that's all bobsled is about. But in this particular one, only 2 of those powerful people are still pushing, and they're not in the sled. So what we have here, okay, is we have to calculate the proper mass. That's the sled plus the pilot and the brakeman. Those 2 guys are in the sled already, okay? They're taking a ride, right? The other 2 guys are doing all the work. They push earlier, okay? They jump in earlier. All right, so we need the combined mass of the bobsled, 225 plus 98 plus 97. Okay, total mass of the bobsled is 420 kilograms with the 2 people in it. Then we have the force of the 2 pushers, 1,200 newtons, 1,220 newtons. And then we have a force of friction that is resisting, that is 430 newtons. Again, gravity and normal force are not very important here because the sled is only moving horizontally. Okay, so can I calculate the net force? Absolutely. Okay, so we'll have our 1,200 plus 1,220 plus negative 430. Okay, so 1,990 newtons is my net force. Okay, so now I've got my net force. Okay, we did our vector sum of all forces. Now we can find the acceleration of the bobsled. F net over m, 1,990 newtons divided by 420 kilograms is going to give us 4.7 meters per second squared forward. Okay, again, nothing mathematically challenging about that, but they're going to get more and more complex as we have to start factoring in forces that are less obvious. Okay, any questions on that one? Okay. All right, got to talk about elevator questions. There's 2 things we get out of elevator questions. The first thing is how to calculate the force of gravity or the weight of an object. Okay, on your formula sheet, you will see this formula. Force of gravity equals mass times g, little g. Okay, little g is 9.81 unless you're told otherwise, like you're on Mars or you're on the moon or something, and g is a different number. Okay, if it's on Earth, we assume it to be 9.81 meters per second squared. Okay, if you're in an elevator, okay, do you feel like different weights in the elevator? Are there times where you feel lighter and times where you feel heavier in an elevator? Okay. When do you feel heavier?
You're slowing down.
Okay, if you're slowing down, yeah.
I like the bottom.
At the bottom, yeah. When you slow down at the bottom, for sure. What else?
You're rising.
When you're rising, when you're accelerating upward. In fact, it's because you're accelerating upward in both of those situations that you feel heavier. When the elevator first starts to descend, you feel a little lighter. Okay, because in order to accelerate downwards, it has to not push on your feet as much. If you were actually standing on a scale in an elevator, which is a classic Newton's second law problem, by the way, people standing on a scale in an elevator, which of course you never see in real life, but it's this like standard trope with Newton's second law questions, you would actually see your weight change. Right? If you were starting to descend, that initial acceleration would result in you looking like you weigh a little less because the floor isn't pushing as hard on your feet as it does when you're just standing there. If it wants to push you upwards, it has to push harder on your feet so that the net force is up. The force up is greater than gravity. That accelerates you up. Okay? The force is less than gravity if you want to accelerate down. Now, do you actually accelerate the whole way down in an elevator? You hope not. Okay, that's bad. All right, if you're accelerating all the way to the bottom, you'll be going very, very fast at the bottom. The acceleration is actually only for the first couple of seconds, unless it's like a really tall skyscraper. So you're going to the top of the Freedom Tower or the Empire State Building or something. They got high-speed elevators that will actually accelerate for like 20 seconds so that they get up to the speed they need to so that you're not in the elevator for an hour to get to work. Okay. But otherwise, yeah, the acceleration is only for the first little bit. Okay, sort of making sense? Okay, so a classic elevator question involves 2 forces. The upward force, which is sometimes called the force of tension because it's a cable, okay, that's lifting the elevator, so there's tension in the cable. Tension is how tight or how hard the cable is pulling upwards. Okay, so that'll be our upwards force. Okay, it can also sometimes be the force of the floor pushing on the feet of the occupant. Sometimes they'll word it that way. It's still an upward force. The downward force is always the force of gravity. Okay, so classic elevator problem, there's a force up, there's a force down. Okay? The force down is always going to be the force of gravity, and you always calculate it by taking mass and multiplying it by the acceleration due to gravity. Okay? So in this particular question, we want to find the acceleration of the person. Would that also be the acceleration of the elevator? It would, because they're together, they're going together. Okay, so the elevator and the person have a combined mass of 600 kilograms. Okay, the elevator cable is exerting a force of 6.5 times 10 to the 3 newtons up on the elevator. So they told me this force, 6,500 newtons. Can I calculate the force of gravity? I can, because they told me the mass of the elevator, right? 600 kilograms. I just go 600, okay, times 9.81, that should be 5,886. Is that right?
Yeah, that's what I got.
Okay,
Eric, you didn't do any work.
okay. So 600 times 9.81 should give me 5,886 newtons. Okay, just looking at this situation, I got 6,500 newtons up and 5,886 down. Which way is the elevator going? Up. Accelerating or moving at a constant velocity? Accelerating. There's a net force, right? The force up is greater than the force down. All right, so we would obviously have an acceleration upwards. Now, most of the trip, the tension in the cable will be 5,886 newtons, and the elevator will travel at a constant velocity. Force up and force down would be equal. Okay, then it'll travel at a constant velocity. But initially, it's got to accelerate. It's got to go from rest to whatever its cruising velocity will be. Okay, so our force upwards is greater than our force downwards. A person inside will feel a little heavier than normal. Okay, and we can calculate that now. So we've done that. We've got our free body diagram. How do I calculate F net here? Sum of all forces. I got a force up, I got a force down. I find their vector sum. So 6,500 minus 5,886 should be 614 newtons, if my mental math is okay there. Okay, and that is up. Can I calculate the acceleration of the person and the elevator? Okay, F net over M, that's going to be 614 divided by 600. So this is newtons up here divided by kilograms. That'll give us meters per second squared. Okay, we have 3 significant digits there, so 1.02 meters per second squared up. Okay. Everybody all right with that? Pretty straightforward, right? Okay, just collinear forces, one up, one down. Now, if we think about this thing, because there's this old like wives' tale / urban legend. If you're in an elevator that's falling, okay, what should you do right before you get to the bottom? Jump. What's that going to do? Absolutely nothing. Okay, all you're going to, you can't even push. Okay, how do you push off the elevator if you're accelerating downwards with it? Okay, and even if you could, you'd break your neck on the roof. Okay, because the elevator's going to stop, and you're going to keep going. You're going to try and accelerate upwards. Well, you're not going to accelerate upwards. Okay, you could try, but yeah, you kind of just got to embrace it. If you're in an elevator that's falling, it might be your time. Okay, jumping at the bottom is not going to save you. I don't know where that urban legend comes from, but it's physically not going to help. Okay? Yeah, they figure, yeah, it'll cancel out. What, you're just gonna defy gravity inside the elevator box for a couple? No. Okay? Plus, the deformation of the elevator will probably crush you inside either way, so, okay, you can rock yourself to sleep tonight with that thought and fear getting in an elevator from now on. Okay? All right, take the stairs, good exercise. Avoid the elevator. All right, making sense? Okay, so yeah, you can think about this, okay, every time you get in an elevator now, you can feel that force on your feet. You'll know I feel lighter because we're accelerating down. I can feel that force upwards. I feel a little bit heavier, okay. In really, really tall skyscrapers, okay, yep, you're gonna have a lot of empty shaft, okay, beneath you. There's actually some of these new skyscrapers that they've built in New York, and they're just like the skyscrapers, well, we'll use that term loosely in Calgary, okay? They're designed to sway back and forth in the wind a little bit, okay? Unfortunately, there's a whole bunch of them in New York they call pencil skyscrapers, and they're designed to sway back and forth, but they sway too much, okay? And they actually can't use the elevators to go to the top floors in winds over 30 miles an hour, because the elevator shaft moves too much and the elevator can get stuck. There's the stuff of nightmares, okay? You bought like a $26 million penthouse apartment, okay, in a pencil skyscraper in downtown Manhattan, and you have to take the stairs to get to it. And when you get there, you get seasick. Okay? You lay in your bed and your whole apartment swings back and forth in the wind. They can't even sell these things. There's a whole bunch of them that are for sale and they can't sell them, okay? Because nobody wants to live in an apartment where they're gonna feel sick all the time. It's kind of crazy. All right, and we'll actually talk more about the design of those in the waves and simple harmonic motion unit, because there's a reason they're supposed to sway back and forth, but they did their job too well. Okay, now, let's have you try number 1 first, and then we'll talk about number 2, because I don't give a lot of questions like number 2, like any, but we'll talk about them. But for right now, same elevator, okay? So the elevator still has a mass of 600 kilograms with the person in it, okay? Important piece of information. Find the acceleration of the person when the cable is exerting that much force instead.
I go to the washroom.
Yep. Okay, so in this question here, we would still draw a free body diagram, right? We would still have our elevator and person, 600 kilograms, right? This force downwards is still the force of gravity. It's still m times g, and it's still the same number as before, 5,886 newtons. Okay? The rest of this question says that the cable is pulling up, but it's pulling up with 5,200 newtons. Okay, that's the force tension, okay, in the cable. This is something that sometimes people have a hard time wrapping their head around. In order to lower the elevator, you still have to pull up. Okay? Otherwise, you're dropping the elevator. There's a difference between lowering the elevator and dropping the elevator. If there's no force upwards, you are dropping the elevator. That's bad for the people inside the elevator. Okay? So to lower the elevator, you still have to pull up. You just don't pull up as hard so that gravity is a little bigger than the force you're using to pull it up. Okay? Like, imagine you have like a crate full of like fine china, and you're trying to, get it to the ground from a roof for whatever reason you have it on the roof. Okay, if you just push it over the side, okay, that's well, you could be the quick way, but you'd have a lot of broken dishes. Okay, you would probably tie a rope to it and lower it down using the rope. Well, to lower it, you still have to pull up. Okay, so there's a force up, 5,200, and a force down, 886 newtons. Okay, so our F net, vector sum of all forces, would be 5,886 minus 5,200. That'll give us 686 newtons down as our net force, and then it's just back to this. A equals F net divided by M. Okay, so that'll be our 686 divided by 600, and that should give us 1.14 meters per second squared down. Okay, remember, it is not doing that all the way to the ground. It's just doing that for the first few seconds to get a reasonable velocity to descend at. Okay, everybody all right with that? Okay, want to look at a relationship here that's kind of important. If I'm looking at that question there, okay, what I said was F net equals the force tension plus the force of gravity. Okay? The other way to look at this is how would I calculate these forces? F net is mass times the net acceleration. Okay? Force of gravity is mass times the acceleration due to gravity. And the force tension would be the mass times the acceleration the tension could produce if it was all by itself. Okay? Everybody okay with that? What cancels out of that? What's in every term there? Mass. Okay? If mass is in every term, can I take it right out? I absolutely could. So what I'm trying to illustrate here, guys, is that net force is the vector sum of all the forces, but this is also true. The net acceleration is the vector sum of all the accelerations. All vector quantities are added in the same way, so that should make sense. Okay, whatever the accelerations would be added together would be the net acceleration. Okay. Everybody all right with that idea? Okay, so that's going to help us to solve question number 2. Okay, we don't give you many net acceleration problems. I certainly wouldn't give one on a test, but it's important to kind of show that this relationship is true. Okay, so I want you to write down number 2, and then we're going to go through it together here in just a second. Looking at this one here, guys. We have the engine, but we don't know what its mass is. Okay, we're just going to write M in there. And then they're telling us that the hoist can exert a force upwards of 2,850 newtons. What other force is involved here? Gravity. Okay, so gravity would be here. Okay, how do I know that in this situation that I should draw gravity smaller than that force? Because it's moving upwards. Okay, the next thing it tells me is the acceleration of the engine is 1.50 meters per second squared up. That means this force has to be bigger than this one, right? And right now, I don't know this force because I can't calculate it yet. It's mass times gravity, and I don't know what mass is. Okay. The other thing I know though is here's the acceleration of the engine. That's the net acceleration. Okay? That's the combination of the upward force and gravity partially canceling each other out. Okay? If it was just that 2,850 newtons, that engine would be flying upwards. Okay? But gravity is holding it back, as gravity always does. Okay? So they want to know what the mass of the engine is. How am I going to go about getting that? Is this still true? So FH will be the force of the hoist. Okay. F net is still the vector sum of all forces, even if I don't have them all, right? If that's still true, I can still write that. Okay. Can I expand this out? Can I say mass times acceleration net equals mass times the acceleration the hoist would produce in isolation plus mass times the acceleration due to gravity? Still true? Still the same thing I wrote the first time, right? Okay, what's in every term? Mass. What can I do with it? Cancel it. Now, probably some of you are going, "Coder, you're losing it," because that's what you're supposed to calculate. What good does it do you to cancel it? Well, here's the good it does me to cancel it. I know what this force is. They told me that force. If I can find the acceleration that force produces, then I can calculate the mass. Okay? Here's how this helps me. I know this number, and I know this number. What's G? You have to whisper. 9.81. Okay, so what I'm going to do is I'm going to cancel off the m's, and I'm going to write 9.8, or sorry, not 9.81, 1.50 equals the acceleration of the hoist plus negative 9.81. Can I find the acceleration of the hoist now? Should be able to, right? I know 2 out of the 3 of these things here. So I'm just going to go 1.50 minus negative 9.81 equals the acceleration that the hoist could produce in isolation. So it was just the hoist. Here's the acceleration its force could produce. Okay? So 1.50, okay, minus negative 9.81. Okay, so if that hoist was the only force acting, the engine would be accelerating at 11.31 meters per second squared. That's huge. Okay, that's more than 1 G. Okay, so now I have the acceleration of the hoist. I have the force of the hoist. Okay, can I calculate the mass now? Okay, so all this, I wouldn't, again, this is not something I would ever ask you on a test, but it's important to recognize that the relationship between vector sum of all forces is also true for vector sum of all accelerations. Okay, sometimes it comes up and it can be important to know. All right, so I'm going to take force of the hoist equals mass times acceleration of the hoist. Now I know that number. Okay. So now I can calculate the mass. All right, so that's going to be 2,850 newtons divided by 11.31. And I'll have the mass of the engine, which will be 252 kilograms. Everybody all right with that one? Okay, this is a differential acceleration question, just like what we just did. Okay, but it has to do with a skydiver. All right, so I want you guys to write that one down and give it a try. Okay, let's have a look at this one. Okay, so we got the skydiver jumping out of the airplane. Again, we don't know their mass. We do know that the net acceleration is 5.96 meters per second squared down. And that would be the result of gravity and air resistance, which is a form of friction. So force of friction acting upwards. Okay. So we want to calculate the mass of the skydiver. All right, well, the force of friction, they tell us, is 250 newtons, so we can do this same thing we did before. If F net is the force of friction plus the force of gravity, then this is also true. The net acceleration is the acceleration due to friction plus the acceleration due to gravity. Okay, I know this number, I know that number. So I'm just going to bring it over here. The net acceleration minus the acceleration due to gravity will give me the acceleration due to friction. Okay, so that'll be negative 5.96 minus negative 9.81. Okay, so the air resistance, or the force of friction, could produce, in isolation, an acceleration of 3.85 meters per second squared up. Okay, now that I know that, okay, since I know that that force of friction was 250 newtons, I can say force of friction equals mass times acceleration due to friction. Just bring the acceleration due to friction over 250 divided by 3.85. Okay, so the mass of that person is 65 kilograms. We have three significant digits. 64.9 kilograms. Okay, for that one. All right, questions on that? Again, I'm not going to ask you a net acceleration question, but as long as you understand that that relationship exists, it can sometimes prove useful. Okay, I would like you guys to try both of those. Okay, number one, there's actually math involved. Number two, not so much. Okay, it's more of an understanding type of question. All right, so give those two a try and we'll go over them here in a few minutes. Okay, is the bungee jumper really just an elevator?
Yes.
Yeah, we have two vertical forces, one downwards, one upwards. It's just an elevator question. Okay, so is me throwing something straight up in the air. That's also an elevator question. I have an upward force and a downward force. Okay? Anything that's just vertical is technically an elevator question. Okay? So in this one here, for the bungee jumper, all right, we know that their mass is 55 kilograms. We know that the force of the bungee cord, so we'll say FB, okay, force of the bungee cord is upwards. We know that it is 825 newtons. Okay, and we know that there's a force of gravity downwards, and since we have her mass, we can also calculate that. 55 times 9.81. Okay, so we're looking at 539.55 newtons. Okay, we have the two forces. Is this the situation you want as a bungee jumper? It absolutely is. The force upwards from the bungee cord is greater than the force of gravity downwards. That will slow you down and keep you from, well, dying. Okay? As long as it's set up right. You don't want to have the cord too long. Then it can exert that force all at once, but if it's too long, it won't matter. Okay, so, yeah, think about that when you decide to bungee jump. Okay? Make sure you can quiz that person on how an elevator question works and what the stretch length and spring constant of that bungee cord are when they're figuring out how much of it to give you. You're putting your life in their hands. Same as the person who packs your parachute, okay? Have a look at that person and decide, do I trust this person with my life? Because you are when you make that decision, okay? So we've got a force up, force down. We can calculate the net force here. Pretty simple question, really. Okay, we'll have our 825 newtons up plus negative 539.55 newtons down. Okay, so we subtract those two for our vector sum of all forces, so 825 minus that number. Okay, so the net force is 285.45 newtons up. We want the acceleration, so we divide that by the jumper's mass, 55. Okay, so the upward acceleration is 5.19 meters per second squared up. Okay, everybody with me there? That is what you want. Okay. Yeah, how many people are done number two? I should probably put all of it up there, right? Okay, so if we're talking about her jump here, it says during a bungee jump, the velocity of the woman at the lowest point is 0 as the cord stretches to its maximum. Is this kind of the opposite of what happens if you throw something up in the air? It is, okay? So you're falling. At first you're in complete free fall. So you're just falling. And then the bungee cord starts to take up, right? Once it starts to stretch, then it can exert that upwards force on you. And you're going to slow down, slow down, slow down. And within a hair's breadth of the ground, for an instant, you stop. And then you get shot back upwards by the force of the bungee cord. So you actually get to fall a couple of times. Okay? When you bungee jump, you get shot back up in the air by the stretch of the bungee cord, and you kind of oscillate a little bit, okay, before they lower you down to the ground. All right? So compare the direction of her acceleration at the lowest point. Which way is she accelerating at the lowest point? Okay, we just said the cord is being stretched, 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 and it's slowing you down. If it's slowing you down, which way are you accelerating? up. That's what you want. Okay, that's what we just calculated. Okay, her acceleration was 5.19 meters per second squared, up. Okay, and your acceleration will be up as long as that force is greater than the downwards force, than gravity, right? But you're going to get to a point where it's going to shoot you up, and then the cord will go slack, and then you will fall again. Your acceleration will be 9.81 until that cord takes up again. So you do a bit of oscillating, okay, in there as you go. Okay, everybody all right with that idea? Okay. Okay. This will lead into what you're going to do tomorrow. Okay, I would like you to copy this one down and label it system question. Okay, so this is our first system question, our system problem. Okay, and maybe leave yourself a little room to write down the system rules. Okay, these are still Newton's second law problems, but there's a couple of rules we have to remember about how systems operate and what a system is. So, first off, what's a system? A system is multiple masses connected. Okay, so a system contains multiple masses connected. Okay. If I have this situation, so I've got a rope. Sorry, I don't want to interrupt.
Are we done here?
Okay, if I've got this situation, so I've got a rope connected to the 10 kilogram mass, the 10 kilogram mass is connected to the 20 kilogram mass, and there's no slack. Okay, if I pull on that rope, do I pull both masses? Do they both move? Do they accelerate at the same rate? That's the trickier one. Yes, they do. They have to. I mean, have you ever seen where, you know, like a semi-truck is pulling a trailer, but the trailer accelerates faster than the truck? That ends badly. Okay, like if a jackknife, that ends badly. Okay, but in this case, no, they have to accelerate at the same rate. They're connected. If they're connected, can I treat them like they're just one 30 kilogram mass? I absolutely can. Okay, so a second system rule is that all parts have the same acceleration. That doesn't have two L's. Okay, all parts have the same acceleration. That's system rule number 2. Okay. Are the individual forces the same? Like, I'm pulling directly on the 10 kilogram mass. Is the tension in this rope the same as the tension in this rope? Which would you have to pull harder on? 30 kilograms or 20 kilograms? 30. Okay? So while these might have the same acceleration, this force is going to be bigger than that one, more than likely. Okay? It has to be because I'm pulling all 30 kilograms. This force is only pulling 20. Okay? So while their acceleration is all the same, and while I can combine them together and treat them as one, if a question asks me about individual forces within the system, they could be different. Okay? So rule number 3, okay, is that masses can be combined or left separate, depending on the situation. Okay, so this first one is a pretty simple system question, okay, because of what they give me. In this question, they tell me that the force in this rope is 55 newtons. That rope is pulling all 30 kilograms. Agreed? It may be directly attached to the 10, but it's also connected to the 20. Everyone okay with that idea? Okay, so I could simplify this because of what they tell me in the next sentence. They tell me that the force of friction on the block system, that is the whole combined 30 kilogram mass, is 44.1 newtons. So really, what the question is telling me is that 30 kilograms worth of mass is being pulled this way by 55 newtons worth of force, okay, and resisted by 44.1 newtons of force. Okay. Both blocks are going to have the same acceleration because every part of a system has to have the same acceleration as the system itself. Okay? There's no one part within the system that can accelerate at a different rate. Otherwise, one of those ropes is either breaking or going slack for no reason, and the 20 kilogram mass will pass the 10. Okay? If the only force is me pulling forward and friction going back, there's no way the 20 passes the 10. Would you agree? Okay. So in this situation, can I just do what we've done on basically every other question? Can I say F net is the vector sum of all forces? Can I say it's 55 plus negative 44.1? That's safe to say? I think so. All right, so that's going to be 10.9 newtons forward. Okay, calculate the acceleration of the blocks. What do I divide 10.9 by? What's my mass for that? Calculate the acceleration of the blocks, plural. 30. Yeah. Okay, so I'd have 10.9 divided by 30 kilograms. Okay, so 0.36 meters per second squared forward. Now, here's how I would mess with you in this question. If I gave you this question on a test, I'd set it up exactly like that, and then instead of asking, what's the acceleration of the blocks, plural, I'd ask, what's the acceleration of the 20 kilogram block? And I'd get a lot of you dividing that by 20 and not 30. Just because of the way I word it. Not because you don't understand the question, but because I mislead you. Okay? And if you forget that whole all parts accelerate, masses can be combined, then you don't get that right. Okay? So it's a system question, and that's how it is going to work. All right, we'll leave it there for today. We'll talk more about systems tomorrow.
Can I ask a quick question about it?